Hello. I expect the microphone's working. It sounds like it is. Great. My name is Bryan Catanzaro. I'm going to be presenting the next session, and I'm visiting from NVIDIA Research. I am a graduate of the Parallel Computing Lab here at Berkeley. I finished my PhD 2 years ago under Professor Koitzer, who gave the talk right before lunch. So coming back here kind of feels like I'm coming home. And it's really fun for me to come back to Berkeley and see some of my old friends around the Parallel Computing Lab and talk about CUDA and graphics processors and OpenCL and some of the things that are near and dear to my heart. I would love to have a more interactive discussion, so if you guys want to interrupt me at any time, I would really appreciate that. I know that sometimes these classes get a little bit on the rails, and so please feel free to interrupt me at any time, and I'll try to give you opportunities to do that. All right. So the overview of what I'm going to talk about today. First, I'm going to go over some terminology and kind of set the stage for why I'm interested in graphics processors and the kind of parallelism that they provide and what programming them is like. I'm going to talk about the CUDA and OpenCL programming models, and then I'm going to talk about understanding how CUDA programs map onto NVIDIA GPUs, which is important if you're trying to get programs to run efficiently on NVIDIA GPUs. Then I'm going to shift gears a little bit and start talking about libraries. Specifically, I'm going to talk about the Thrust library, which I think is the way that everybody who's learning how to do parallel programming should start, especially when they're dealing with GPUs. It's a little bit higher level, and it's a lot safer and a lot more likely to lead to good results right off the bat. So, all right, so let's dive in. So, when we talk about graphics processors and we talk about parallel computing, what we're really talking about is heterogeneous parallel computing, where we have two kinds of processors bound together in the same system. And we have a latency-optimized CPU, where we have a few cores, each of which are optimized for fast serial processing, maybe somewhere on the order of 4 to 16 cores. And we have that combined with a throughput optimized GPU where we have many cores, lots of cores depending on how you count, anywhere from tens of cores to thousands of cores. And they are optimized for scalable parallel processing. So the difference is latency versus throughput. Latency, is defined as the time it takes to finish one task. Throughput is defined as the rate at which we can complete large numbers of tasks. So they're kind of different problems, and they result in really different architectures. For example, here's comparing two different architectures. We have, on the left, we have from Intel a great processor, the Sandy Bridge EP. It has 8 cores, each of which are 2 issues, so they can issue 2 instructions per cycle. And each of those can issue 8-way SIMD. And I'll get to SIMD in a second, but you can think of that as an additional dimension of parallelism. And it's running at 3 gigahertz. If we talk about the amount of threading that this processor has, each of those 8 cores has 2 resident threads that it can issue instructions from. And so if we multiply that out by the number of SIMD lanes that it has, we're talking about on the order of 96 strands of parallel execution resident on the processor at any given point in time. So let's contrast that with the Tesla K20 GPU from NVIDIA. This is our latest and greatest architecture, the Kepler architecture. This has 14 streaming multiprocessors, each of which are 6 issue, and each of which are 32-way SIMD. And it's running much slower, only at 730 megahertz instead of 3 gigahertz. If we look at the number of contexts resident on the chip, so each one of those streaming multiprocessors can hold 64 SIMD vectors. And each of those SIMD vectors, like I said, was 32-way SIMD. So when you multiply that all out, that's about 30,000 threads that's sitting on the chip at any given time. Question in the back. They're 32-way. So the question was, how wide are the SIMD vectors? And the answer is they're 32 wide. And I'll get into how that's actually reflected in the programming model. But the way that it works is when you write programs for GPUs, you write a single thread that gets replicated across the machine, and those threads get mapped onto SIMD lanes of the hardware. So you don't actually vectorize your code explicitly. The hardware and software does that for you. But what I'm getting at with this slide, this comparison of 96 versus 30,000, is the scope of parallelism that you need in order to keep the chip busy, right? So with a latency-optimized chip, a latency-optimized architecture, you need, order of 100-way parallelism in order to keep the chip busy, in order to keep it all fed. With the throughput-optimized machine, you need quite a bit more parallelism. And we're going to use that parallelism in order to get increased performance. So if you look at the single precision gigaflops, we're about an order of magnitude higher. And we can sustain that because we have quite a bit more memory bandwidth. Another interesting thing to note is that the memory hierarchy is kind of inverted. So a traditional memory hierarchy from a latency-optimized core, we have the register file, which is, if you aggregate over all 8 cores on this chip, it's about 128 kilobytes of register file. And then we have the L1 cache, which, again, in aggregate is about 256 kilobytes. And then we have the L2 cache, in aggregate, about 2 megabytes. And then the L3 cache, shared amongst all the cores, is about 20 megabytes. So you have this sort of pyramid that everything is sitting on, whereas you go out farther away from the cores towards the memory, you get larger and larger memory capacity. On this throughput-optimized processor, we see actually the opposite. So the register file in aggregate is 3.5 megabytes. The local store / L1 cache is about 896 kilobytes, and the L2 cache is about 1.5 megabytes. So it's kind of like an inverted pyramid. And the reason why the register file is so large on this throughput machine is to support all 30,000 of those contexts in flight at any given time. And the reason why it has so many contexts in flight is to hide memory latency. So when you're executing a program and it needs to go to memory, the throughput machine assumption is that it's just going to suspend that thread while it issues its memory instruction and switch to another program that has its context also sitting in the register file and start executing instructions from that program. And then later on, when the memory instruction returns, from its long trip to DRAM and back, it'll switch back to the original program. So it's very highly multi-threaded, and that gives us the throughput that we need. That's the reason why we can sustain such high memory bandwidth and arithmetic bandwidth as well. But it's a very different kind of architecture and requires different programming, different algorithms. And that's what my talk's going to be about today. All right. So why heterogeneity? And I've been getting at this, but I'll just state it again. So different goals produce different designs. Throughput cores assume that the workload is highly parallel from the beginning. And graphics cores, they were built from the ground up. Their day job, the reason why they exist, is to play video games, right? And when you're playing a video game, you're running a program for every pixel of the screen that you're drawing, right? And every one of those pixels is more or less independent from all of the other pixels. And so you have millions of independent programs to run. And the latency that it takes to draw one of those pixels doesn't really matter. What matters is the throughput at which you can render all of those pixels. So that's why we end up with this throughput architecture. Latency cores assume the workload is mostly sequential. That's the reason. That's what's driven traditional processor performance over the past 50 years. Is increasing sequential workloads performance, and so that's why we've ended up at these different design points. I'm going to skip this because we've already sort of mentioned it. All right, so let's talk about SIMD for a little. And SIMD is kind of interesting because although I've been talking about heterogeneity and how things are really different, SIMD is something that's actually becoming increasingly important both for traditional CPUs as well as for things like GPUs. And I'll get to that in a second. So SIMD architectures make use of data parallelism. in a single instruction, single data model, for example, you have one instruction that says, let's take A and let's take B, and we'll add it together and make C. A single instruction, multiple data architecture, this little cartoon assumes a SIMD width of 2, will take two vectors of A1 and A2 and B1 and B2, and we'll add them together to produce another vector of C1 and C2. So the reason why that's called data parallelism is that we're parallelizing over the data, right? We have these input vectors and we have an output vector, and the elements in those vectors are independent. But the reason that it's good for the hardware is that independent gives us area and power advantages because we can amortize control overheads. So this is very efficient. On the other hand, now this parallelism is exposed to the programmer. So you and I, when we're writing our applications, we need to figure out how to take advantage of that. And that can be sometimes a little tricky. And I would argue that SIMD parallelism is neglected parallelism. So if you've seen talks about other parallel programming models during boot camp, many of them have not talked about SIMD parallelism. For example, OpenMP or pthreads or MPI. SIMD parallelism is usually neglected when these programming models are discussed. And SIMD parallelism is treated as something orthogonal, like you parallelize your program using MPI, and then you make sure that each of your threads uses SIMD intrinsics to use SIMD parallelism inside of each one of those MPI processes. And that's because it's difficult for a compiler to automatically exploit SIMD, because it's hard to deal with sparse data and branches. How do you automatically vectorize across your data structures, especially when you have languages like C that are difficult to auto-vectorize. So commonly, what people have done in the past with SIMD intrinsics on traditional CPU architectures is they've forgotten about SIMD and prayed that the compiler would just automatically do something, which sometimes works. Or if you really care about it, you instantiate intrinsics, which is almost like assembly language. You're calling very low-level functions that explicitly instantiate the instructions that you want. And that requires a new code version for every SIMD extension, of which there have been quite a few. So this is a brief history of x86 SIMD extensions, starting from MMX, which came out when I was in, I guess I was in junior high school when MMX came out, so that means probably a lot of you were not born yet. It was in 96? Okay. All right. So we have some people that remember when it came out. So there's this long line, and as time has gone on, there's been an increasing set of capabilities that each of these SIMD instruction sets has provided, like adding floating point, adding double precision floating point, adding horizontal ops across SIMD vectors, increasing the width of the vectors, adding 3 operand instructions. The current, recently Intel announced AVX 3.x, which sort of unifies the Xeon Phi instruction set with the AVX instruction set that is used in traditional x86 cores from Intel. And so those are pretty wide SIMD instructions that have a lot of capabilities. But what I'm getting at is that there's quite a lot of these, and if you want to write intrinsics for all of these, it's a lot of work. But it's important, using SIMD is important, and some people are starting to call this many lane parallelism. When you have wide SIMD vectors, like the 16 wide vectors that we have with the newest version of AVX from Intel, if you don't use SIMD at all, you're throwing away 94% of the instruction bandwidth of the machine on, say, floating point operations. Back when SIMD was only 4 wide, if you threw away 75% of the floating point bandwidth of the machine, it's probably not so important, because who amongst us can write code that runs at more than 25% of the peak performance of the machine anyway? That's it's pretty hard to notice that. But as SIMD becomes increasingly important for every architecture, both for CPU and GPU, this problem of how do we write programs that use SIMD instructions, SIMD parallelism, becomes more important. And so we need a programming model that makes using SIMD easier. And this problem composes with thread-level parallelism. So when we talk about using pthreads and OpenMP and these other kinds of parallel programming models, this composes with SIMD because this is kind of expanding the type of parallelism that we also need to address. And so ideally what we would have is a programming model that lets us deal with all these different kinds of parallelism together. And that's exactly what CUDA does. So the CUDA programming model is designed for heterogeneous architectures that have many SIMD lanes and are very scalable. So we can write the same parallel program and it runs on something with a very small amount of parallelism or a very large amount of parallelism. And the way we get that is a thread abstraction to deal with SIMD. So instead of writing SIMD intrinsics that target particular SIMD vector lengths, we write threads that are going to be mapped onto SIMD lanes. And then we write our code in terms of small blocks of threads where the size of these blocks is bounded. And we are going to promise that we'll only synchronize and share data between threads in these small bounded blocks. And the guarantee that we get, because we've made that promise, is that the hardware is going to be able to map these blocks onto the hardware efficiently, and we're going to get scalability. So CUDA programs are written in C++ with a few minimal extensions that I'll go over. And CUDA came out in 2006, and a few years later was followed by OpenCL, which is inspired by CUDA and has a very similar programming model. And so I'll go over sort of the connections between those. So from what I understand, you guys have the option of doing a homework assignment for this boot camp in either OpenCL or CUDA. And so hopefully you'll be able to use these slides as a resource when if you elect to do that homework assignment. I'm not going to go over all the details in these slides because some of them are kind of just intended to be used as a reference guide, but they're there in case you want to refer to them. Okay, so let's talk about the CUDA programming model. So we have a hierarchy of concurrent threads. We're going to write what we call a kernel, and it's going to be explicitly parallel. So from the get-go, we're not writing a sequential program, we're writing a parallel program, and all of the threads of this parallel program are going to start out at the same place. These threads are going to be grouped into thread blocks, and threads in the same block can cooperate. And every thread and every block has a unique ID that we can query. So we can say, which thread am I and which block am I? And we can use that to do things. So what is a CUDA thread? It's an independent thread of execution. It has its own program counter. It has its own variables that get put in registers. It has its own state. It doesn't have any implication as to how the threads are scheduled. So they might be physical threads as they're mapped onto NVIDIA GPUs, and I'll talk about that later. They might be virtual threads. So for example, if I was compiling a CUDA program to run on a latency optimized core, and there exists a product out there from PGI that does this. You can compile a CUDA program and run it on an x86 CPU, for example. You might actually want to run a thread block on one physical thread on a CPU. So because the CUDA thread doesn't specify exactly how it's executed, there's some flexibility as to how it's actually mapped onto hardware. So what is a CUDA thread block? A thread block is I think of it as a data parallel task. All of the blocks in the kernel, when you launch it, they're going to have the same entry point. So they're going to start out at the same place. But after that, they can execute any code they want. The important thing is that all of the blocks in the kernel need to be independent, and your program has to be valid for any interleaving of block executions. And I'll get to what that means in a second. So what are the kinds of parallelism that we can support? We support thread parallelism because every thread is independent. We support data parallelism because a typical way of using this model is to launch threads across the data that's intrinsic to the problem that you're trying to solve. We can support task parallelism because the different blocks are independent. So it's really easy to do something like, if my block is block number 0, then do task number A. If my block is block number 1, then do task number B. And we can also launch kernels in separate streams. So the CUDA runtime provides this notion of a stream where you can launch kernels or memory copies or other runtime things into different streams, which is an explicit guarantee to the runtime that these requests are independent and they can be executed in parallel on the hardware. And so that's a form of task parallelism. All right. So let's talk about synchronization. There are two primary ways that CUDA programs synchronize. The first one is that threads within thread blocks. So thread blocks, remember, are restricted scope. So these are small, like say 1,000 threads. And 1,000 threads may seem like a lot of threads if you're used to programming for CPUs, but for a CUDA program, 1,000 threads is very small because we usually launch programs with like 1 million threads. That's totally routine. So like within a small group of threads, you can synchronize with a barrier. We call it sync threads. And what that means is that all of the writes from all of the threads in the block have to be visible to all of the other threads in the block by the time the sync threads is complete. So that means that you can communicate because you can have, say, thread n-1 in the block do some work, and then thread 0 in the block can read that work and use the result of that computation to do something else that it needs. So those barriers are very useful. Skip to the last bullet. The other primary way that we get synchronization in CUDA is with an implicit barrier between dependent kernels. So when we launch a kernel onto the hardware and then we follow it with another kernel launch, these are sort of like parallel function invocations, there is an implicit barrier that says all of the writes that were performed in the first kernel need to be completed before the second kernel launches and need to be visible by every thread launched in the second kernel. So that is also a form of synchronization. The third form of synchronization, which is a little bit more sophisticated, is that we can coordinate operation between blocks using atomic memory operations. So CUDA provides a restricted set of atomic memory operations, such as atomic increment, that allows blocks to, for example, append things to a shared queue, where everybody could, for example, as they're working, they're maybe computing some data-dependent set of items. When they discover that they actually have an item that's interesting, then they can atomically increment the tail pointer of a queue and use the result of that increment to figure out the slot that's reserved for the item that they're going to add to that queue. All right. So blocks need to be independent. Any possible interleaving of blocks should be valid, and the blocks are presumed to run to completion without preemption. So they can run in any order, they can run concurrently or sequentially. So you can't really assume when you're writing the program that block number 0 and block number 1 are concurrent at the same time. And that gives us scalability because a CUDA program can run on a processor with 1 core on it, or it can run on a processor with 30 cores on it. And the exact same binary needs to be able to run on both. So this independence assumption gives us that scalability. And because this blocks can coordinate, so like I said, they can have a shared queue pointer where everybody's working together to add stuff to a shared queue. But things like shared locks, for example, are a lot more tricky because you can't assume that another block is actually concurrent at any given time. And if you write code that assumes that any other block is actually concurrent when you are, then you can easily deadlock. But this independence requirement gives us scalability. Like, for example, I took this snapshot of chips that existed in the market at a given point in time, like several years ago, and there was a 30-fold variation in the number of cores that we were shipping in our product line, and you can target all of these things with the same binary, and that's because we have thread blocks. Because when you write in CUDA, you write with thread blocks, and the thread blocks get multiplexed across the chip dynamically, and when you write your applications using thread blocks, you automatically get scalability. So that's pretty great. Oh, yeah. SM stands for streaming multiprocessor. The SM is kind of the indivisible unit of computation on our architecture, so I treat it kind of equivalently to a core. The marketing department at NVIDIA treats it equivalently to a lot of cores on our current architecture. They call it 192 cores. So they would say that like our latest and greatest GPU has 3,000 cores on it or something like that. That depends on how you count things. But I would say that an SM equals a core. It's just our cores are really wide, and they have a lot of SIMD and a lot of execution resources. So. All right. Okay, so after telling you how great CUDA is, let's look at a program. So this is kind of the hello world of data parallel programming, vector addition. So we're going to compute vector sum, C equals A plus B, and we're going to launch one thread per element of vectors A and B and C. And let's see. So how are we going to do this? So first we're going to figure out which index we are as a thread. So we're going to pick up our thread index in the block, and that's thread index.x. So the block ID and the thread ID is a three-dimensional space, so you can launch like three-dimensional thread blocks and three-dimensional grids. So that's why there's a .x on there, because you could put .y and .z. But in this case, we're just going to launch it in a one-dimensional configuration. So that's why it's all .x in here. So .x, and then we're going to figure out how many threads there are per block. So that's blockdim.x, and then multiply that by our block index.x. And when we add all those things together, that's going to give us a unique index for our thread, and we'll call that I. And then we will do the sequential code to do like one, basically the loop body of vector addition, right? So Ci equals Ai plus Bi. All right, so who wants to tell me what's wrong with this code? What could possibly be wrong with this code? N might not be divisible by 256. That's a good point. I'm looking for one more thing that's wrong with this code. Somebody else mentioned cache blocking. That's pretty advanced. I'm not going to talk about that quite yet. There's a correctness problem with this code that may lead to a segmentation fault. Can anybody find it? The size of my vector. I didn't check, right? So I assumed that I launched exactly the number of threads as there were elements in my vector. But what if my vector was size of 2 and I launched 1 million threads? Then what would happen? Well, I would get a segmentation fault. So, right. So typically what people do, at least what I do when I write code like this, is I'll along with these parameters, like these pointers that have the data, I'll also give it a length, and then I'll say if I is less than length, then do the work, otherwise do nothing, right? So you sort of guard your work by the length to make sure that you're safe. Good, you guys figured it out. Also, so I should mention the code in main that actually launches the work. So we have this magic triple chevron thing here that has 3 angle brackets. That is the CUDA parallel function launch. And what we're saying here is launch n over 256 blocks of 256 threads each. And somebody else in the audience mentioned that n might not be divisible by 256, so that would be also another problem with this code. What would happen if n is not divisible by 256 with this code? What would the error look like? You'd run, yeah, so basically you wouldn't launch quite enough threads, right? Because in C, the division function ends up being a floor, and so like you would end up launching slightly too few threads, and you wouldn't finish the work. So when you actually launch code yourself, you'll need to be a little more careful about how many threads you launch. But this code, other than those 2 caveats that I mentioned, this code is complete. Yeah?
Did you say that you would pass in a length variable?
I would, yes.
Can't you check the length and just see that you already passed in, or do you not pass in? Does it not pass in the full vector?
So the question is, does it not pass in the whole vector? So if you look at the way that we've passed in the vector, we've actually passed them in as pointers. And so a pointer in CUDA is just like a pointer in C. It doesn't carry any information about length. And so you can dereference it with an offset, but that doesn't guarantee that the dereference that you've done is valid. So if it is still within like the bounds of the memory that you allocated, then you'll be fine. And if it's not, then you'll get a segmentation fault, which, if you've ever done C programming before, you know that segmentation faults are difficult to debug. And it's the same with CUDA. So I guess the other thing that we need to talk about is the memory spaces. So when we talk about these pointers here, what do we mean by these pointers? So let's talk about that. So the memory model is that every thread has a per thread local memory, which is where like the stack goes, right? That you're used to having. We also have per block shared memory that's going to sit on chip. Yes, question?
On the previous slide, don't you have to transfer the memory to like CUDA memory first before you do the computation?
Yes. So the question is about transferring data to CUDA memory first. I'm going to get there in just a moment. So good question. You're anticipating my next slide. Thank you. Uh-huh. So in CUDA, all of the launch parameters are runtime variables. So in this code, we're giving you something simple here. So I think n being capital here makes it look like it's compile time constant. But the runtime accepts arbitrary runtime things in there. All right, so there's a per block shared memory, and the per block shared memory is going to sit physically on the chip, and it's going to be the primary space in which threads are going to communicate inside of the block and share data, and it's going to be really important for performance. Then we also have a per device global memory. So this is very high bandwidth memory that sits on the board with the GPU. And data can persist in that memory across kernel boundaries. So when we launch a kernel, data can sit there. When we process stuff, the results can sit in memory. And when we're finally done, that's where the result of our computation is going to reside. We also have a divide between host memory and device memory. So host memory would be your typical memory that you use with any other program. And device memory, we then bridge with a CUDA mem copy, an API call. Okay, so then here is the rest of that program with the code for actually allocating the data and transferring it. So here we are saying what n is. And we call malloc to allocate data on the host. And then you'll notice we have similar calls for allocating data on the device. And we use CUDA malloc instead of the standard malloc, but otherwise it's fairly similar. The interface is slightly different, but otherwise it's pretty much the same. Then we use something called CUDA mem copy, and that's going to move data. You notice that one of the parameters is the size of the data movement that we want to do in bytes. And we're going to move it from the host to device. Then we call the kernel. And then we call CUDA mem copy to move the result back from the device to the host. So that's kind of the hello world about managing data. OK, so we have a few minimal extensions to C and C++. We have this global __ global __ that shows a kernel that's callable from the host. We have __ device _ that shows a function that's callable from the device. We have decorators for variables that live in device memory or in per block shared memory. We have a function invocation syntax for parallel kernel launch. We have a few special variables for thread identification that I've already shown you: the thread index, block dimension. And then we have synchronization for the barrier. So that's pretty much it. So how do we use per block shared memory? This is really important for performance reasons because per block shared memory sits on chip, and memory bandwidth is really, really crucial to performance. So when you write CUDA code, oftentimes a common idiom is that you're going to copy data into on-chip memory, and then you're going to do some computation that shares that data, and then you're perhaps using sync threads to communicate, and then you're going to write out the result. It's faster than the L1 cache. It's slower than the register file, but it's relatively small. The register file is bigger. Okay. I'm going to skip over this because we're running out of time. Okay, so now I'm going to talk about OpenCL. So OpenCL is very similar to CUDA. It's supported by AMD CPUs and GPUs and NVIDIA, as well as Intel CPUs and Intel Xeon Phi, and some other people like Imagination Technologies that makes mobile GPUs are on board. The data parallel model is very similar to CUDA's. It has something similar to shared memory. It has something similar to threads, although they call them work items instead of threads. It has something similar to thread blocks, but they call those work groups instead. It has kernels. They call those kernels. It has a rich task parallelism model that's a little bit more developed than CUDA's. And instead of just having kernels that you launch sequentially, you can actually build up a dependence graph of kernels and memory transfers. And I've put this correspondence between terminologies. So you can refer to this if you're writing OpenCL code. So they're pretty much equivalent. I'm going to skip this. I'm going to skip this as well. All right. Let's see, because we're quickly running out of time. All right. So when we're doing performance tuning for GPUs, the first thing that I think is important to focus on is memory concerns. So Kathy Yellick, a professor here at Berkeley, said a many-core computer is defined as a device that turns a compute-bound problem into a memory-bound problem. And if you think about it, it makes a lot of sense because when you have so many cores, so many compute units that are sitting on a die and they're sharing the same interface to device memory, there's just one socket, lots of processors. So memory concerns really dominate performance tuning. And so we need to be careful about how we use memory bandwidth. And a throughput-oriented machine, it's going to be about throughput. So memory throughput is going to be your most precious resource. And it turns out that memory is SIMD2, not just instructions. And that has effects on how you write your code. In traditional processors, we talk about cache lines. When you fetch, say, for example, element 0, the processor goes out and fetches a bunch of other elements just on the chance that you might need them later. So the group of elements that it catches is called the cache line. And this has two effects. Sparse accesses waste bandwidth. So if you grab elements just 0 and just element 0 and element 4, you'll load 2 words, but you'll ask for 2 words, but the hardware will load 8 words. So you'll get a quarter of effective bandwidth. And unaligned accesses can waste bandwidth as well. So if you ask for elements 1 through 4, it'll still load elements 0 through 7, and that'll give you half the effective bandwidth. So that means that sometimes it's good to take care of that with your data structures. So you want to make sure that your arrays are padded and use your data structures wisely. So you may need to transpose arrays of structures into structures of arrays. That can be a really useful transformation to perform. Okay, so sorry, I'm going on kind of a whirlwind pace because we're really running out of time, and I wanted to get to this. I think this is a really important part of the discussion here. When we talk about programming parallel machines like GPUs, the performance landscape is exposed to the programmer. So, it can sometimes seem daunting. There's a lot of different optimizations to try out, and sometimes efficiency can seem in tension with productivity, right? The more efficient you want your code to be, the less productive you are as a programmer. I actually think that with parallel programming, we're starting to see the opposite, that the best way to get productivity is to use libraries that are efficient. The best way to get efficiency is to use libraries, and that makes you productive. And to think about it this way, have any of you ever tried to write a matrix multiply that's faster than a matrix multiply from Intel? It's pretty hard, isn't it? It's really, really hard. Intel has a group of people that are really great at what they do, that optimize MKL libraries and get really great performance on those libraries. They're highly parallelized. They use SIMD very well. Yeah?
Did you say that the ArrayFire library, is that a good library to use? Because I saw that on the NVIDIA site, and I ended up using that in my research, and it basically turned all my code like MATLAB code, and it was super fast. Is that efficient, or should I implement my own gradient function, or is it okay to use that?
So I haven't used the ArrayFire library myself, but from what I've seen, it looks pretty good. I think things like that are really important, because I think that's the way that sort of parallel programming is going to be democratized. That's the way that we programmers are going to get both efficiency and productivity, is by using libraries, higher level libraries. So just to give a concrete case study. So somebody came to me a couple weeks ago and said, I have this k-means clustering code. This is a machine learning algorithm. And I wrote multiple thousands of lines of code of OpenCL, and they showed me 50 slides of all of the stuff that they had done to make it go fast. And they're like, but my code still isn't very fast. And I had to use this really complicated hybrid reduction that was half on the CPU and half on the GPU. And gosh, getting it correct took me forever, and it's just not very fast. And so I tilted my head for a second and rewrote it using a library called Thrust, as well as cuBLAS, which is NVIDIA's basic linear algebra subroutine library, and a few very, very simple unoptimized CUDA kernels, the most brain-dead simple kernels that you can think of. I didn't optimize them at all on purpose, and yet the whole thing went 60 times faster than the code that this other person had spent a long time writing. And I put the link up there so you can go look at it and see what this code looks like. And I'm holding this up as an example of what happens when you use libraries instead of trying to write the code all yourself. So as parallel architectures proliferate and their performance landscapes continue to get more complicated, it just makes more and more sense for us to use higher level libraries instead of trying to write everything from scratch ourselves, because the chances of us getting lucky and actually getting something to work efficiently in a finite length of time, it's just unlikely to happen. So use libraries. There's a lot of good libraries out there, and I want to talk about one that's called Thrust, which is a library for C++. It mimics the standard template library. It works for GPUs. It also works for CPUs. It has parallel backends using Intel's thread building blocks and OpenMP. It has algorithms like sorts and scans and reductions. And this is what code looks like. So instead of using, for example, CUDA malloc in order to allocate memory and then CUDA memcopy to move the data back and forth, look, for example, at this third line of code that says thrust device vector dvec equals hvec. That one line of code does the CUDA malloc and the CUDA memcopy for you. It also does exception handling for you. So let's say there's not enough memory on the GPU device memory for instead of giving you back a null pointer, which maybe you forget to check because let's be honest, sometimes us sloppy programmers forget to check error messages. Thrust will throw an exception, which then will show you on your command line standard bad alloc uncaught exception, and your program won't continue for how long you didn't catch the exception, giving you incorrect results. So this kind of thing is really much more productive, and I say much more pleasant to use and much more stable. There's a lot less chance to sort of cut yourself by accident on the sharp edges of sort of these lower level runtimes. Then, so for example, this call to thrust sort, the work that went into making thrust sort run at, I think that 846 million keys per second is outdated. I think the result now is more like 1.5 billion keys per second on the same hardware. That represents, a PhD thesis from a really talented person. And it's available to you. All you have to do is call the right library. So Thrust, it's a great library. It's really easy to use, and it immediately unlocks the power of parallel hardware without you having to know the low-level details right away. Is there a question back there?
Yeah, before I get too excited, does it have complex numbers?
Let's see. So I believe that there exists an implementation of complex numbers that works with Thrust. And you can email me about that, because I know I've seen a lot of people on the mailing list doing stuff with complex numbers, but I haven't ever done it myself. You can't use standard complex with it directly, because you have to overload the operators with host and device tags in order for it to work with the Thrust algorithms. But somebody's already done that, so there's a library that you can download that lets that work. So the question was, does Thrust work with complex numbers? You can define your own types using standard C++, and they'll work with Thrust. Okay, so another thing that Thrust lets you do, which this is really awesome. So before we were talking about pointers, CUDA pointers, if you dereference them on the host by accident, will give you a seg fault, because the CUDA pointer is in a different memory space from the device, from the host. Now, Thrust device vectors, on the other hand, you can dereference from the host. And so this line of code that says dvec bracket 0 equals 13, that will actually instantiate a CUDA mem copy for you behind your back. You don't need to know about that. You just assign to it. And that's due to the magic of C++ types, right? So the way it works is that Thrust device vector is a special type, and it has an operator bracket method that it's been overloaded in the appropriate way so that it can call CUDA mem copy if necessary. And similarly, the other way around. So when it says dvec 0, and you're dereferencing it, the data that's sitting on the GPU memory, to print it out onto the to standard C out, you can just do that. Yeah. The assignment operator, yeah. Yeah, all the operators have been overloaded, so it is really nice. We are working at NVIDIA to get this into C++ 17. We're partnering with Intel and Microsoft in order to do that. I'm sure there'll be some changes, so it won't look exactly like this. This is open source. It's on GitHub. Yeah, GitHub. Yeah. And it's also shipped as part of CUDA, so every CUDA installation comes along with Thrust automatically. You don't have to download it. It's just already there.
How old is this stuff? How stable is it?
It's very stable. It's been developed since 2007 or something like that. So, yeah, I use it every day. It's the only way that I do CUDA programming. The primary developer is Jared Hoberock, and he's in my group at NVIDIA Research.
So is it being supported by NVIDIA?
It is. It's part of the CUDA distribution. Yeah. So Thrust uses iterators like the STL. So you call reduce. So like reduce is going to give you, like, for example, the sum. of all of the elements in the range between two iterators. So writing a parallel reduction, if you've never done that before, that can be a non-trivial exercise. Calling thrust reduce, really easy. Iterators are kind of like pointers. You can increment them, you can dereference them, you can subtract them. Let's see. I'm going to skip over this. The kind of algorithms that Thrust has, we have transforms. So like element-wise kernels, you can just call Thrust transform. So typically, instead of writing like an element-wise kernel in CUDA and launching it with the triple angle brackets, I just call Thrust transform, for example. We have reductions, reduce by key. We have scans. We have sorts, sort by keys. So, for example, this line, these 4 lines do the CUDA vector addition example that we were talking about earlier. So here we are allocating 3 vectors, A, B, and C. We just say they all have size 10 in this case. And then here we are calling transforms. So we have a pair of iterators that define the range of A begin and A end. And then we're also pulling from B. And then we have the output range from C. And then we give it the functor that we're going to launch across all these elements, in this case, plus. We could instantiate with a different functor like minus if we wanted to do a vector subtract. We could do, for example, a multiply reduction if we wanted to multiply all the elements of a vector together. Just instantiate reduce with, instead of a plus that's like adding all the elements together, we could instantiate with a multiplication to sort of multiply all the elements together. Let's see, I'm going to skip this. So here's a sort of example on how to write your own operator. So this negate operator, it's working on a custom type. So I think you had a question on how would it look to use complex numbers. So in this case, he's working on float2, which is kind of like a complex number. So he's writing a struct that negates both of the components of a float2. So you'll notice that the struct, it has an operator parentheses, sort of the call operator. It's been overloaded. And it's tagged with both host and device, which means that this functor can be used both on the CPU as well as on the GPU. And this functor is just going to negate both components of that float2 vector. So when he calls transform at the bottom, that's going to instantiate that functor across all elements of the input vector. And it's going to run on the GPU because it was instantiated on device vectors which live in the GPU memory space. Now, if he had declared those as host vectors, those would instead be parallelized using OpenMP and running on the CPU. Yeah? It would rely on whatever the host compiler was able to do with SIMD. So your guess is as good as mine as to whether the host compiler would be able to auto-vectorize that with OpenMP. My guess is that it wouldn't, just because my experience with auto-vectorization has been poor. But maybe it would. Maybe it's gotten better since I tried it last. Let's see. There's no support for MPI at the moment. It's OpenMP and TBB and CUDA are the 3 backends. You can use your own custom types. You can interoperate. So if you want to get a pointer and use it with a CUDA kernel, you can do that. Let's see. I'm skipping because we've run out of time. The point here of these slides is just that it's a lot less work to write Saxby, instead of like having to explicitly deal with parallelism and decompose it into threads and blocks, you just write a functor that deals with it element-wise and then call transform. So it can be a lot easier. Instead of having to write a new reduction every time, which in serial it's not too hard to write a reduction every time because it's just a single loop with one line of code. If you're writing a new parallel reduction for every data type and for every operation, that's just really terrible because it's like thousands of lines of code to write a parallel reduction tree. But if you use thrust reduce, you can instantiate it with whatever data type you want and with whatever reduction operator you want, as long as it's commutative and associative, and you're fine. Sort works really well. Like I said, sort, this is the result of somebody's careful PhD thesis. This is just showing that if your data types are good data types like floating point numbers or integers, it will use radix sort. And depending on the distribution of your keys, it will actually do early exit if your keys don't have a lot of entropy in them. So your sorting rate will actually improve significantly if, for example, all your numbers lie within a bounded range, because it will figure out that the sort is done early. So that's pretty cool. That's the kind of thing that it takes pretty sophisticated knowledge of how sorting algorithms work in order to do by yourself. But if you call thrust sort, you should get that for free. Sort plus reduce by key is a really powerful idea. So reduce by key allows you to combine elements with the same key into the same value. So that's it's kind of like a poor man's map reduce. I used it, for example, in that k-means routine that I was talking about earlier. And Thrust is online. There's a quick start guide. There's examples and mailing lists and everything. All right, so we're out of time. What do I want you to take away from this lecture? I think throughput optimized processors complement latency optimized processors. We need both. They have really different architectures. They're designed to solve really different processors, and they end up with really different programming models. CUDA and OpenCL are the low-level ways that we target GPU-like processors. They abstract SIMD, which I think is a neglected form of parallelism, but increasingly important, both for CPUs as well as GPUs. But I would say for all of you that are considering programming GPUs, starting out with something like Thrust is a lot more productive and likely to get you going a lot faster than actually starting out with CUDA. And in general, I would say libraries will get you a lot farther, and I would recommend that you start out there. And with that, I'll take any questions. Yeah?
If I have a cluster with the GPU managed, can I then run GPU code and then reduce, like as a map, for example, and then reduce those using an API?
Right. So the question is, if I'm running on a cluster with a GPU per node, how do I deal with the GPUs? And the answer is yes. You have to use MPI the same whether you have GPUs or not. GPUs are kind of orthogonal to clusters. There's no specific tools that come along with GPUs that help you manage clusters. So you do whatever work that you need to do on the GPU using the GPU programming tools that you have, and then you use MPI to deal with cluster level issues. Yeah. So we'll take that question and then yours.
I've heard rumors on the internet that the next generation of game consoles seem to have a shared memory CPU, GPU style architecture. Thoughts? Good thing? Bad thing?
So the question is that the next generation of game consoles have a shared memory system between latency optimized and throughput optimized cores, whether that's good or bad. I think it's a good thing. I'm excited about that. Especially, I was particularly happy that the Sony version had GDDR5, so that's sort of a throughput optimized memory. I think, if you marry throughput optimized cores and latency optimized cores on the same socket and then pair that up with latency optimized memory, that just makes the throughput optimized cores really sad, right? But if you pair them up with throughput optimized memory like GDDR5, then that seems really interesting. And NVIDIA is. So at SIGGRAPH a few weeks ago, we demoed our latest Tegra processor that has a full-blown Kepler GPU on the same die as our ARM CPUs, and you can run all CUDA programs on that GPU, sharing the same memory. So yeah, we see that happening as well. Yeah, next question.
So in January, CUDA wasn't compatible with Ubuntu like 12.10, but now I just noticed just now that it is compatible with 12.10. Does it? But I upgraded 13.04. Does it work on 13.04?
The question is whether CUDA is compatible with Ubuntu 13.04. I haven't actually tested it. I assume that it is. I've actually had good luck installing CUDA on, versions of Ubuntu that aren't officially supported, and it's worked for me. But your mileage may vary, so be careful. But yeah, there's always some play. I think the biggest problem with Ubuntu is that it installs open source graphics drivers that conflict with the NVIDIA closed source graphics driver, which is often necessary in order to run CUDA applications. So be careful with that. Because sometimes you can boot and your system is like unresponsive and you don't know why. And it's usually because there's two drivers fighting. So, yeah.
Just on a related note, I was at a conference and was talking with the VMware folks and complaining to them that I couldn't use my, I have a 560 board, and they told me that they were going to come out, I guess now it's about 4 months ago, with a VMware version that'll be compatible with your products. So I don't know if that's true or not right now.
Well, so I haven't used that particular product, so I can't say like whether or not it's actually on the market. But I do know that there's been a lot of interest in that, and I certainly hope that they come out with that because it would make a lot of people happy. So,
yeah, well, myself.
I mean, really, the work involved in doing that is fairly straightforward, right? They just need to be able to pass the driver commands through their virtualization layer. So, at least it seems straightforward to me, but what do I know?
Just one question is Thrust. Is that supporting the latest CUDA 5?
Yeah, it's part of every CUDA distribution since like CUDA 3.0, I believe.
So it's always revved with the...
Yeah, the latest and greatest Thrust is always available at GitHub. So the version that comes integrated with the CUDA distribution is going to lag a little bit, but you can always download from GitHub. Thrust is implemented as a C++ header library, so there's nothing to compile. There's no installation process. It's pretty easy. All right, well, I think we're out of time. So thanks, everybody, for your interest and questions.